Swayam Prabha. Digital India. Educated India.
Good morning. Today we will study one of the most important lessons of applied mathematics, and that is numerical solution of ordinary differential equations. In many courses and many textbooks of differential equations, you might find that the analytical solutions of differential equations are discussed first, and then it is said that in all cases you may not be able to solve the differential equation analytically. In fact, in majority of cases you will not be able to solve, and in such situations we must resort to numerical solutions. However, we prefer to precede the discussion of analytical methods by the solution of differential equations by numerical means. The reason is that this is most general, and this is the way of historical development of the field also. That is, first the initial attempts were in terms of finding the values of the solution function, and it was later found that in certain situations the solutions can be expressed in terms of closed form expressions in special cases. So, in those special cases where such an analytical solution is possible, we can do much more than getting just values, but it is the values of the solutions which have the prime place in terms of the determination of the solution of ODEs. So, we follow that methodology, that sequence of operations. First, we try to find the solutions in the most primitive manner in terms of numbers, and then we will examine how sensible are the resulting numbers, and then we will consider those special cases in which analytical solutions are possible. So, first we start with numerical solution of ordinary differential equations. This will be our last topic in the module of differential equations, and this we in the module of numerical analysis, and it will be a bridge between the module on numerical analysis and the next module, which is going to be on differential equations. So, this topic we will cover through 3 lectures starting from the current one. First, we consider the straightforward problem of one differential equation in one dependent variable, one function, one independent variable x and one dependent variable or function y, unknown function which we want to determine. Now, this is a first order differential equation in y with an initial condition given, that is, at one value of x the value of y is given. So, this makes it an initial value problem. The initial value of y is given at x0, and then for all subsequent values of x, that is greater than x0, we want to find out the values of y. For that matter, we could have asked for the values of y for x values which are less than x0 as well, it is equivalent. So, we want to determine y of x for x in an interval a to b, with a being the initial value of x, that is x0. Now, this is in a way somewhat analogous to an integration problem. Why? Here we have got dy by dx and we want to find out y. So, it is in a way integration, and therefore, you will find that the numerical solution of ODEs have a lot of similarities with the numerical integration problem. Only major difference is that this side, the dy by dx, is not dependent on x only, but it is dependent on x as well as y. So, a first order differential equation, first we put in this form in which we get the expression for dy by dx in terms of x and y. Now, if we are lucky, if it just happens that this function turns out to be free from y, then it is a straightforward integration. On the other hand, if it is dependent on x and y, then we cannot solve the problem just by an integration. So, in that case, what we can do still is that we may say that we will take a very small step to begin with. Okay. So, starting from point x0 y0, we will ask first that just a little ahead of x0 at x0 plus h, what is the value of y, that is at x1, what is y1. So, we have x0 y0 a point starting point, and we want the next point x1 y1, where x1 is only slightly ahead of x0, that is x0 plus h. Now, for that very small interval, if we can consider this function not to change significantly, then what we can say? We can say that the value of that function we evaluate at x0 y0, and that derivative, that slope, we multiply with the small change in x, that is h, and that gives us the corresponding small change in y, and that delta y we add to the current y0 and get next value of y, that is y1. So, that gives us a point x1 y1. Now, we know that y of x1 is y1, and dy by dx at that point we will be able to find out from f of x1 y1. F is a known function. So, we go on repeating these kind of small steps up to x equal to b. This is indeed a method, and shortly we will see that this is a method with a given name, and on that we can do certain analysis and so on. So, before proceeding for that analysis, we have a quick look at the two kinds of methods which we can use. One is a single step method, in which only the current value, only the current x0 y0 and the corresponding f is used at every iteration. And there is another family of methods which is called multi-step methods, in which history of several recent steps are used. Okay. So, that kind of a method is called a multi-step method. Most of our discussion here will be limited to single step methods. Okay. Now, resuming the discussion of this method. This method is actually called Euler's method, and at every step this is the methodology. At x and yn, evaluate the slope by this, and for a small step h, use that value of dy by dx, multiply that with small change in x, which is h, and that when you add to the current value of y, you get the next value of y, and this way repetition of such steps will construct the function y of x. That is, for x equal to x0, x1, x2, x3, x4, etc., you will find the corresponding values of y, y0, y1, etc., and those points in the xy plane will give you the trajectory, and that will be the solution of the differential equation. Now, if we construct the truncated Taylor series, first order truncated Taylor series on of this function, then we will find that the expected error of this Euler's method turns out to be of second order, that is order of h square, because up to h we are actually retaining the change. So, up to from h square onwards there will be errors. So, leading error term will be h square over every such small step. That means that from a to b, as we go on taking large number of steps, that is, if we have divided the interval a to b into n parts, each part of size h and so on, in that case these kinds of errors will get accumulated, and then the accumulated error, as we saw in the problem of numerical integration, will be of one order higher, one order lower, that is up to linear errors. So, these are at every step we will have an order h square error. So, accumulated over steps the error will be larger. Okay. Larger means lower order of h, h is a small step. Okay. So, the total order of the error, total error order will be order h. which is bad, because it is first order error. Error will be in the first order itself. Okay. So, that means that if you use Euler's method, you are likely to have a lot of errors. First order error means that unless h is extremely small, you will find that the error is significant and the result is not very reliable. Now, one question that we should ask at this point is that, is the total error over say 10 steps like this will be the sum of errors over the 10 steps? Now, the answer is not so in general. The total error may be larger than the sum of the individual errors, or for that matter it could be smaller also. It depends upon the differential equation under question. So, how that happens, that total error could be larger than the sum of errors or smaller, and what can be done to improve this error, that we will explore next. First of all, consider this situation: dy by dx equal to f of x y with an initial condition given at x 0 the value of y is y 0. This is the initial point, initial condition, and as if we could solve the correct solution of the differential equation, and if we could have got y as a function of x, then suppose y as a function of x, for that the graph is this, shown by the curve C. Now, if we take a small step h and move to x1, then here now I will enlarge this and try to show. In this enlarged figure, you can see better, that is, this curve, the top curve is the true solution. Now, as we start from the given initial condition x 0 y 0, then with the Euler's method we will be proceeding along the current slope, that is, whatever is the slope of the curve, that means along this direction, and wherever this tangent cuts the vertical line at value x equal to x1, that is x 0 plus h, we will get that point. Now, from that point, in the next step of Euler's method, the current tangent will be used, and that means that along the current tangent, that is a tangent here, we will be proceeding towards this. Now, note that first of all, we have, because we moved along the tangent, we have left this true curve. Currently, we are sitting at curve which is this curve, second curve from the top. Now, since we will be moving along the tangent from this point, in this step, that is in the second step, we will be leaving this curve also, and we will be actually landing up at the third curve from top, that is, we will be leaving C in the first step, reaching C1, then at the second step we will be leaving even C1 and reach C2, the next curve, and so on. Now, note that the error in the first step is this y intercept from the true value at x1 to this value where we reach, and the error at the second step will be actually must be counted along this, that is, this is the true value for the second step, because it was trying to track this curve and it has reached here, that means the error is this. Now, this error in the second step plus this error in the first step will actually be somewhere here, that is second step error plus first step error, and the actual error is from here to here, which is larger than the sum of these two. Now, the sum of these two can be found if you draw a line from here parallel to this tangent, that is somewhere here. Okay. So, in this particular example, the error of the first two steps is actually smaller than the total step, that is individual errors, error in the first step plus error in the second step, compared to even this sum, the overall error, accumulated error in the two steps is even larger. Okay. So, this way errors not only accumulate by simple sum, but might even magnify. In another example, that could have been lesser than the sum. Now, what is actually happening? We find that this way at every step we will be leaving the initial curve, and then we will be leaving the next curve, and then we will be leaving the next curve, and finally, after 3 steps we would have actually got to a point which is the solution of the same differential equation with the initial condition y at x0 equal to so far below the bottom curve, wherever the bottom curve crosses that value of y. So, this way this will be the total error in 3 steps. So, that shows that with first order error getting accumulated, the total error over a large number of steps may be a bad thing in the case of Euler's method. Now, what is the reason? While exploring the reason for this, we also ask a question that from x0 to x1 we moved during the entire h along the slope which was given at the initial point, right. Was it a good idea? The slope changes from this point to that point. If the slope changes from this point to that point, then how good is the idea of moving all the time with the same slope as given in the initial point? If we could figure out some average slope, then that would have given us a good move. Now, with that intention, the Euler's method is modified, and then we have what is called modified Euler's method or Hume's method. Now, in improved Euler's method or modified Euler's method, what is done is that a first step is taken. Now, the problem is that it would be nice to be able to take an average slope, but then how do we know the average slope? To begin with, we know only the y value here and therefore the slope here. At the end point or in the middle point of the interval, we do not know the y and we do not know the slope. Now, in improved Euler's method, what we do? From here we take one tentative step and reach q1, okay, reach q1 along the slope here. After that, we say that it was perhaps not a good idea to move from here with this slope only. Now, let us calculate the slope here. After we have got this tentative point at x1, we have got some value of y1, call it y1 bar, okay, and then we evaluate the slope here from the same f of xy. At this point, we evaluate the slope. Then we say that along that tangent with that slope, the new slope here, we draw a line, suppose that goes here at p1. Then we say that what is the difference between p and p1? This difference. Now, we say that if rather than with the slope here, if we had started with the slope here and moved, then where would we have reached? That is, rather than along this slope, but with this new slope which we have now evaluated, if we had moved, then we would have reached q2. But then q1 is wrong because it gives complete weightage to the initial slope. Similarly, q2 would be wrong on the other side because that would be giving complete weightage to the final slope. The true picture should lie somewhere in between. So, what about taking the average of q1 and q2? That is q. That is given by improved Euler's method or Hume's method, and this is the analytical formulation. That is, from the value x n y n, take one tentative step and call that value of y at x1 as y1 bar, yn plus 1 bar, and then evaluate the step if we use that slope, that is f of xn plus 1 yn plus 1 bar. With that, you will have the step as h into this. Now, this is one proposal and h into this is another proposal. So, what about the average of them? Average will be h by 2 into this plus this. Okay. So, this is the point taken for this step. Now, this also will have some error, but if you make an analysis based on Taylor series, you will find that the corresponding error is second order over the complete domain, over the complete interval a to b, that is accumulated error, that will be of second order. So, that makes sense because we have made two function evaluations at this point and at this point, and we have got a second order method. Now, this can be continued with 4 function evaluations. We can land up at a fourth order method, and actually there is a family of methods called Runge-Kutta methods. So, second order Runge-Kutta method generally would go like this. First estimate k1, which is same as Euler, k1 is estimate for delta y. Second estimate, now here we say that we do not make the evaluation at this end point, but somewhere in between, that is in between x and x0 and x1 somewhere, where that we decide by alpha and beta, that is alpha step from here and beta step in the y direction. So, if we do that, then we get this point where we can evaluate the slope function, and based on that we work out the second proposal for the change in y, that is delta y, and then say that we have got the first proposal from here and the second proposal from here. What about taking a weighted sum of the two? Now, in this particular case, the weights W1 and W2, you will expect that W1 plus W2 should be 1, otherwise this will not make very good sense as a weighted sum, and take that k. Now, we ask what weight values we should use, and for that we try to force agreement up to second order, that is h term in the error and h square term in the error we try to force to 0 to get the appropriate values of W1 and W2. How do we do that? We say that based on this, if we try to work out yn plus 1, that will be yn plus this k, W1 into this, that is W1 into HF, plus W2 into K2, that is this, okay, W2 into K2. Now, if we try to work out a Taylor series of this, a truncated Taylor series of this, then we will get f at x and yn plus alpha h into first derivative with respect to x plus beta k1 into first derivative of this function with respect to y, okay, plus higher order terms. Now, if we simplify this and collect HF terms together and then h square terms together, then we get this, right. This is the Taylor series of yn plus 1 which we are getting. Now, at xn plus 1, the Taylor series value of the original function y at xn plus 1 without this formula, that would be yn plus h into dy by dx, which is this, plus h square by 2 into d2y by dx square, which will be this by chain rule of this function, that is this, and so on. Now, when we compare these two, okay, when you compare these two, we get the error, and in that we say that we want the error to have 0 value up to the second order. That means first order error should be 0, first at up to first order this should match, and second order also these two should match. So, the first order terms here and here, if you match, then you get W1 plus W2 equal to 1, which you would expect, and then as you equate the second order terms, you get this also, that is alpha into W2 should be from here 1 half, and when you equate these two, you get beta into W2 is half. So, there are 3 equations here in W1, W2, alpha, beta. If you try to solve them, 4 unknowns from 3 equations, you can get 3 of the unknowns in terms of 1 remaining unknown W2. Now, depending upon which value of W2 you select, you may get slightly varying second order Runge-Kutta methods. It is a family of methods. Now, if you take W2 equal to half, and that will mean that alpha beta will turn out to be 1, okay, then you get what we just now discussed, that is improved Euler's method. On the other hand, popular choice of second order Runge-Kutta method is W2 equal to 1, okay, which means that you take the first proposal as Euler's method, and for the second proposal for delta y, that is k, you evaluate the function at the midpoint of the chord of the step that has been taken. At that midpoint, you evaluate the function and thereby work out the second step, second proposal for the step, and then take the second step only, not the first step at all. Okay. So, that will mean that W2 is 1 and W1 is 0. This has been used only as a stepping stone for evaluating this function, and after that this is not used at all. The actual step has been taken equal to K2. So, this is second order Runge-Kutta method. Similarly, with 4 function evaluations, you can get a fourth order Runge-Kutta method. Now, this point onwards, I am not trying to derive or prove, but without proof, let us state this, that if you work out the first proposal as based on the initial value, just like Euler's step, and second proposal of delta y, that is K2, as we have just now done, and then the third proposal as K3, which is this, in which in place of this k you use k1, you use k2, the fresh one, and finally the last evaluation is made with full step h and k3, and for delta y here you use the most recent estimate. Okay. And then you have got 4 different proposals for delta y and take this weighted sum 1 by 6, 2 by 6, 2 by 6, 1 by 6, sum is 1. Now, this particular arrangement of the 4 possible delta y's ensures that the error over an interval up to 4th order is 0. That means, over a particular sub interval over a particular step h, the error that the leading error term that you will get will be h to the power 5. That is only up to 5th order, only from 5th order there will be errors, and that means over accumulated over several steps for the entire domain, the error will be 4th order, and that is why this method is called 4th order Runge-Kutta method. With 4 evaluations of the function, you get a 4th order method. However, you can work out higher order methods also in the Runge-Kutta family, but then for getting a 5th order Runge-Kutta method, it is not enough to make 5 function evaluations. However, with 6 function evaluations, you can work out a 5th order method. That particular arrangement has some further merits, which we will be discussing a little ahead. Now, through whichever method, whether it is a 2nd order method or 4th order method, you develop the solution of the ordinary differential equation, how do you figure out whether the resulting value is right? That is, what is the magnitude of the error, which is really important in a practical situation? How do you determine the magnitude of the error? So, this is, and in particular whether the error is within tolerance. For that purpose, you can do 2 things. One is, you can make an additional estimate which will give you a handle to monitor the error, and based on that you can develop further efficient algorithms. That is, whatever best you get with a particular order of method. So, if you have additional estimates, then you can develop an estimate of the error, and on the same basis you can develop further efficient algorithms. That is, you can reduce the error as well as you can know how much is the error. So, it is very much like what we did with Richardson extrapolation in the case of the numerical integration process. Suppose in a particular interval from xn to xn plus h, you have developed one particular estimate of the value at xn plus h, that is yn plus 1, one estimate. So, we are showing it as with this superscript 1, and that is the correct value plus some error. Now, if you have used the 4th order Runge-Kutta method, then the leading error will be 5th order, right, plus higher order terms. Now, what you can do is that you can now evaluate the same yn plus 1 not with one step of size h, but 2 successive steps of size h by 2. Then the corresponding second estimate will be yn plus 1 plus 2 such steps. So, twice c into this coefficient is same, constant is same, c into the h by 2 to the power 5, because every step is now of h by 2 size. So, in the first step you accumulate c into h by 2 to the power 5, in the second step also that is the estimate. So, 2 half steps will give you this error. Okay. Now, note that here you have got 2 equations in the true value and c. H you know, and these 2 estimates you have got through the RK4 formulas, Runge-Kutta 4th order formulas. So, these left sides you know and H you know. So, you have got 2 equations in yn plus 1 and c. These things you do not know. Now, 2 equations in 2 unknowns, linear equations in 2 unknowns you can solve. So, as you solve that, you find that difference of the 2 estimates will throw out one of the unknowns, that is yn plus 1, and give you this is c h to the power 5 and this is c h to the power 5 by 16. So, difference is 15 by 16 Ch to the power 5. So, this gives you the difference of two estimates. And what is the error here? Error here is Ch to the power 5 by 16, that is 1 by 15 times this, right. So, you have got an error estimate, that is error estimate of the second value. Obviously, this value is better than this, okay, because this is with one step of this size, this estimate is based on two half steps. So, this is a better estimate, and in this the error is Ch to the power 5, which turns out to be from here related to the difference of the two estimates, right. So, difference of the two estimates will be giving you 1 by 15 of the difference of two estimates is Ch to the power 5 by 16, which is the error estimate here, right. So, if you use that, or if you multiply this with 16, multiply this with 16 and take the difference, then also you get the same result. In any case, between these two equations you can solve for Ch to the power 5 by 16, which is the error estimate, and the true value or the best estimate till now, that is yn plus 1. So, this is the best available value out of these two estimates. So, this way you get two things. One is an estimate of yn plus 1, which is better than both of these, which you get like this, and two, you get an error estimate of this, that is Ch to the power 5 by 16, which is the difference of these two divided by 15. So, now you can say that if that is within your required accuracy, within your tolerance. So, if you find that the delta that you are ready to tolerate is quite large, that means if delta is quite large compared to the epsilon value which you are ready to tolerate, then that will mean that the current step size is too large for accuracy. So, in that case you subdivide the step further and take smaller steps. Okay. On the other hand, if the delta that you get is much less than epsilon, that means what? That means the error is within tolerance, but perhaps you are taking too small steps. Even larger steps would be all right to solve the problem within the required accuracy. But then you have already determined so many function evaluations you have already made, that means computational step you have, computational resources you have already spent. So, now you cannot do anything further to save that computational resources spent. So, that is why at the starting you should keep the step size not too small, reasonable step size, not too small. And if you find that at some location the delta that is coming with this estimate is too large, then that particular step you subdivide further. Okay. So, start with a large step size, not extremely large, but reasonably large, okay, and then keep subdividing intervals whenever you find delta is greater than epsilon. So, that will mean that suppose you want to solve this from this initial point to this final point. So, this is x0 where the value of y is given, this point. Okay. So, what you can do? You can say that initially this entire interval from x0 to say final x, okay, this entire domain over which you want the solution of the ODE. So, you can say that I will try to solve it with 4 steps. So, this step you find that you develop one estimate and another estimate, based on that you get a third much better estimate and an error estimate. Now, find out whether that error estimate is acceptable. If it is acceptable, then take the best value that you have got till now. Similarly, you try to do it for this step, and suppose here again from this point you find that you have got one estimate, second estimate, and based on these two you get a third much better estimate, and at the same time an estimate for the error. Now, suppose in this case the error turns out to be too large, then you say in this location this step is going to turn out to be too large. So, you subdivide and do the same thing for this and this. So, now over this small step you operate and get this. next whatever. So, whenever you find that the error estimate shows that too much error is coming, then subdivide the interval further, otherwise continue. Okay. So, this ensures that you keep on marching fast over those segments of the function where the function is smooth, and those segments where you get quick changing, fast changing situation, there you make small steps, and where to make the small step, that this delta will tell you. So, this is what is called adaptive step size algorithm. Now, another interesting thing, another interesting feature of Runge-Kutta method is that, as we discussed just now, that with 6 function values we can get a fifth order formula, fifth order Runge-Kutta formula. Not only that, using a different combination of those 6 function values, you get another formula which is a fourth order formula. Now, with this situation, with 6 function values, a fourth order formula is found embedded in a fifth order formula, and this helps you in 2 ways. That is, you get 2 independent estimates of the value of y n plus 1 and an error estimate based on the same 6 function evaluations, and this is called Runge-Kutta-Feilberg method, and most of the professional implementations use that RKF45. However, if you are a beginner in this kind of implementations, then, and if you want to implement your own solution of ODE routine, then I would suggest that RK4 itself, fourth order Runge-Kutta method itself, with these straightforward formulas, is also going to be quite effective for your purposes with adaptive step size, which we just now discussed. However, if you call a library subroutine, then most likely you are going to get an RKF45 routine available in most of the important libraries, numerical libraries. Now, till now we have been discussing a single first order equation. Now, but then whatever we have been doing is directly applicable to a first order vector ODE. If x remains scalar, but y becomes vector, and therefore f of x y becomes vector function, even then all the operations that we have been conducting can be still conducted. That is why whatever we have been discussing in the context of a single first order ODE can be immediately extended to a vector ODE. That means a system of first order ODEs like this. Okay. Of course, in that case the initial condition has to be available for all the y's. Okay. So, the entire y vector has got an initial value, initial vector y0. So, this can be solved with the help of same formulas, only with the change that y's become vector, x remains scalar still. Okay. However, if you have a higher order differential equation, then an nth order ordinary differential equation can be always converted into n first order ordinary differential equations. For that, the way is to develop the equations in the state space. That means that you first define a state vector including the unknown function, its first derivative, second derivative, up to n minus 1th derivative, if the ODE is of nth order. That is, if the ordinary differential equation involves derivatives up to nth order, then the state vector will involve derivatives up to n minus 1th order, one order less. Okay. So, this vector completely defines the state of the system that the differential equation is trying to describe, and then you try to work out dz by dz, dz by dx, partly from this definition and partly from the differential equation. How? You see here, z1 is y. So, dz by dx is going to be y prime, which is z2. Then y prime, now z2 is y prime. That means dz2 by dx will be y double prime, which will be next entry, that is z3. That means from here to here, except the last one, z1 prime will be z2, z2 prime will be z3, and so on till z n minus 2, z n minus 1 prime will be z n, this one, this is z n. Okay. Z n prime will be the nth derivative of y, and that you get from the differential equation. Okay. And initial conditions also will get this kind of values, whatever is the values given for y, y prime, y double prime, etc., up to the n minus 1th derivative. So, those will form the initial condition for z, and then you solve the system with the same RK4 formulas, etc., So, in general, if you have got a number of ordinary differential equations, each of order higher than the first, then also you can follow the same procedure and break down the entire system into a large number of first order differential equations. In general, if you have got a system of higher order ODEs with higher order derivatives of the unknown functions y1, y2, y3, y4, etc., being n1, n2, n3, n4, etc., then you can cast the entire system into the state space form with the state vector of dimension n1 plus n2 plus n3 plus n4, etc. Let us take an example. So, this state space formulation is directly applicable when the highest order derivatives can be solved explicitly. For example, let us take this example. This is a system of two ordinary differential equations in two unknown functions x of t and y of t, which we want to solve. So, we want to solve for x of t and y of t. So, two unknown functions. So, we have got two differential equations, right? And what is the highest order of derivative of x that is involved here? Up to second order, right? Similarly, what is the highest order of derivative of y that is involved? Up to third order. Okay. So, in the state space, we will have x and dx by dt. This we will not have in the state space. That is, if up to the nth order derivative is involved, then up to the n minus 1th order derivative will appear in the state vector. So, d2x by dt square is there as the highest order derivative of x. So, in the state vector we will have up to dx by dt. In y, we have the third order derivative of y as the highest order derivative. So, the state vector will have y dy by dt, d2y by dt square, that is up to second order derivative. So, the state vector will be x dx by dt, this will not be there, the highest order derivative will not appear. Similarly, from y we will have y dy by dt and the second derivative of y, not the third one, because the highest order derivative will be actually found, will be solved from the differential equation itself. Now, see what you have got. Three derivatives of three of the components here will be trivial, because z1 is x. So, z1 prime will be dx by dt, which happens to be z2. So, z1 prime is z2. Similarly, z3 is y. So, z3 prime will be y prime, that is dy by dt, which happens to be z4. Similarly, z4 is dy by dt, its derivative z4 prime will be second derivative of y, which happens to be z5. So, that is this. So, these three derivatives are trivial. We need to find out what is z2 prime and what is z5 prime. So, that you find from here. Okay. From this differential equation, from the above first differential equation, you can write y z2 prime minus 3 z4 z2 square plus twice z1 z2 square root of z5 plus 4 equal to 0, right. Just match term by term. We have written this differential equation. Y is okay. In place of y, actually we can write z3. In place of y, we can write z3. So, just go on reading this first differential equation in terms of these as z1, z2, z3, z4, z5. So, y is z3, look up there. Then this second derivative is z2 prime, that is prime of this, minus 3, then dy by dt that is Z4. Okay. So, Z4 here, and then we have got dx by dt whole square, that is Z2 square, plus twice Z1 and then dx by dt, which is Z2, and then square root of this, which is Z5. So, square root of Z5 plus 4. So, from this differential equation, can we not find Z2 prime? We can find Z2 prime. We take this whole thing on the other side of the equation, divide by Z3. So, as we take this whole thing on the other side of the equation, we get this, and then we divide this whole thing with Z3. Of course, this will be valid in a domain in which Z3 does not become 0. Okay. So, Z2 prime turns out to be a function of Z1, Z2, Z3, Z4, Z5, right, and we have already found that Z1 prime is Z2, and we have already found that Z3 prime is Z4, Z4 prime is Z5, and Z5 prime we need. Okay. So, for finding Z5 prime, that is the derivative of this, which is here actually. Okay. So, we do a little further work in this box here. The second differential equation from here we write in the language of z's from here. So, e to the power xy, okay, e to the power xy. So, x is Z1 and y is Z3. Into d3y by dt cube, right. So, that is Z5 prime, which we want to determine, is equal to, sorry, minus, or we can take is equal to and write the other things with the changed sign. Z3 Z5 to the power 3 by 2 minus 2 Z1 minus 1 minus e to the power minus t. Do we get that? Plus. Okay. So, just read off this, e to the power xy there, e to the power Z1 Z3 into this third derivative, which is the prime of Z5. So, Z5 prime is equal to, so these things will take on the other side, y, that is Z3, into d2y by dt square to the power 3 by 2, that means Z5 to the power 3 by 2. This also goes to the other side, minus 2x minus 1 minus 2 Z1 minus 1 plus e to the power minus t. So, that is here. So, that means that we can solve for Z5 prime as this. Now, you see the prime, the derivative of the vector function z, that is Z1 prime, Z2 prime, Z3 prime, Z4 prime and Z5 prime. All these 5 are available in terms of the 5 z's and t. That means, together we can write the vector z prime as this function with these 5 components in the same standard form, right. So, that is this form, and this is the state space equation. So, this is how we can formulate a system of higher order ODEs into the state space form, and then use the same numerical methodologies that we discussed for the scalar single function. Now, apart from these single step methods that we have discussed till now, there is a family of methods for which use several earlier steps results as well. For example, in single step method, every step of h is taken as a brand new initial value problem, in which the current value is there, and from there we try to develop the slope function and take one step. Now, can we not try to capture the trend by learning from the history of several recent steps? That is a kind of thing that is done in multi-step methods. So, a typical multi-step formula for solution of ODE is this, that is in which you take yn plus 1, that is the next value of y as the current value plus h into a sum of several function values, a weighted sum of several function values. Okay. C0 into f at the next point plus C1 into f at the current point plus C2 into f of the at the previous point plus C3 into f at the yet earlier point, and so on. So, this is a typical multi-step formula. Now, based on what do we determine the coefficients C0, C1, C2, C3, etc.? We say that we want the leading error terms h, h square, h cube, h to the power 4 as 0, 0, 0, 0. So, as the leading error terms are forced to be 0, that gives us a system of linear equations in the coefficients C0, C1, C2, C3, and those coefficients are used in a multi-step formula. Now, you will say that we cannot use a multi-step formula at the first step, because at the first step all that we have is this, starting from there x0, y0. Before that there was no step, no function evaluation. So, that is why a typical multi-step formula can be used as a multi-step formula only after the single step results have been accumulated. So, they have to be started with single step formula method, single step methods, and after some steps have been developed, then only this kind of a formula can be used. Now, there are two kinds of multi-step formulas. One is explicit, where C0 is 0, that is the next value yn plus 1 is explicitly available in terms of the current and old values. Okay. On the other hand, if C0 is not 0, then the corresponding method is called not an explicit method, but an implicit method. That means yn plus 1 has been expressed in the form of a function which involves yn plus 1 itself, and from that to determine yn plus 1 we really have to solve an equation in yn plus 1. So, that kind of a method is called an implicit method. So, it is of course not explicit. So, it is difficult to evaluate, requires a solution of an equation, okay. But such methods have better stability. And so far as the issue of stability is concerned, in the next lecture we will discuss the issue of stability in more detail and talk of implicit methods in comparison to explicit methods, even in single step formulas, the kind of formulas that we have been discussing so far. And the most famous, most popular multi-step formula is called the Adams-Bashforth-Moulton method, in which there is a solution predicted using the Adams-Bashforth formula, and the solution is then corrected using another formula, which is the Adams-Moulton formula. So, this combination of a predictor formula and a corrector formula, by which you first predict and then make a correction. So, that kind of a predictor corrector formula is used in multi-step method, and if you need multi-step methods, then you can look up further literature on this kind of methods. So, for the time being we stop here with this little summary over what we have discussed in this particular lecture. One is the basics of Euler's and Runge-Kutta methods, and the second is the one of the very important professional practice of step size adaptation for really nonlinear problems, in which you use the step size in an efficient and effective manner without wasting too much of computational time. And the third important thing in this lesson is the state space formulation of dynamic systems, with the way to reduce higher order differential equations or their systems into larger number of lower order, larger number of first order differential equations, and then develop the state space formulation in this manner, which can be then numerically solved. So, This state space formulation is a necessary precursor to any numerical solution of ordinary differential equations. In the next lecture, we will consider advanced issues of ODE solutions. We will discuss stability analysis and the utility of implicit methods and their specific usefulness in the case of stiff differential equations, and then we will continue into discussing boundary value problems in ordinary differential equations. Thank you.